Look up at the night sky tonight, and you're not just seeing stars, you're staring into a time machine. Every flicker of light is a message from the past, some so ancient they predate the dinosaurs, the formation of Earth, even the birth of our sun. But what if I told you the universe doesn't just send us these signals, it sometimes reflects them back at us, like a cosmic echo? This is the strange and beautiful world of deep time reflections, where the fabric of reality bends light so profoundly that we catch glimpses of the universe's earliest moments, as if it's peering back at us across the ages. Think about the last time you stood between two mirrors, watching your reflection repeat into infinity. Now imagine that on a scale so vast, the mirrors are galaxies, and the light trapped between them has been traveling for billions of years. These aren't just optical illusions, they're windows into the past, created by gravitational lenses warping space-time itself. Einstein predicted this phenomenon over a century ago, but even he couldn't have imagined the eerie snapshots we'd uncover. Distant stars multiplied, ghostly arcs of light, and entire galaxies stretched into smudges of primordial history. It's as if the universe left breadcrumbs for us to follow, clues hidden in the way it twists and distorts its own light. So why does this matter? Because every reflection, every bent beam of starlight, forces us to rethink what we know about time, space, and our place in the cosmos. These aren't just pretty pictures, they're proof that the universe has a memory, a way of preserving its own story in the most unexpected ways. And today, we're going to unravel that story together. From the mind-bending physics behind gravitational lensing to the philosophical questions it raises if we can see the past, does that mean the past is still out there, somehow? This journey will change how you see the night sky. By the end, you won't just look up at the stars, you'll feel them looking back. To grasp the sheer scale of deep time, picture this: if the entire history of the universe were compressed into a single calendar year, the Big Bang would strike at midnight on January 1st. The Milky Way wouldn't even form until March. Dinosaurs would appear and vanish in a single day in late December, and all of human history would flash by in the last 14 seconds of December 31st. That's the humbling reality of cosmic time, where entire civilizations rise and fall in less than a cosmic blink. Yet somehow, the light from those earliest moments still reaches us, carrying echoes of events so ancient they defy imagination. These photons, particles of light that began their journey when the universe was young, aren't just relics. They're active storytellers. Take the Hubble Space Telescope's famous deep field image, where a seemingly empty patch of sky revealed thousands of galaxies, some so distant their light took over 13 billion years to reach us. That means we're seeing them not as they are today, but as they were when the universe was a mere toddler, a fraction of its current age. It's like finding a letter written at the dawn of time, preserved perfectly in the darkness of space. But here's where it gets stranger. Because the universe is expanding, that light doesn't just tell us what happened. It shows us how space-time itself has stretched over eons. The wavelengths of these ancient photons lengthen as they travel, shifting toward the red end of the spectrum, a phenomenon called redshift. This cosmic fingerprint lets astronomers map the universe's growth, tracing how galaxies drift apart like raisins in rising bread. And when gravity bends this light, creating those eerie reflections we call gravitational lenses, it's as if the universe folds time like a piece of paper, letting us peek at multiple eras at once. So what do these time-warped glimpses reveal? They show us a cosmos far more dynamic than we once thought. Quasars, supermassive black holes devouring entire stars, shine with the brightness of a trillion suns. their light amplified by intervening galaxies acting as natural telescopes. Supernovas, the explosive deaths of stars, replay like cosmic reruns as their light takes different paths around massive objects, arriving at Earth years apart. Each reflection is a puzzle piece, helping us reconstruct the universe's grand timeline. Yet deep time isn't just about the past, it reshapes our future too. By studying these ancient light echoes, we're essentially reading the universe's autobiography, learning how it grew, changed, and perhaps most hauntingly how it might end. Will expansion continue forever, leaving galaxies isolated in an ever-cooling void? Or will gravity eventually pull everything back in a big crunch? The answers might already be written in the light streaming toward us, waiting for the right moment to be decoded. Every time we look up, we're not just observers. We're detectives sifting through the universe's oldest evidence, piecing together a story written in starlight. Light is the ultimate time traveler, carrying stories from the universe's farthest reaches straight to our telescopes. Each beam that reaches us is like a cosmic postcard, stamped with the date of its origin, sometimes from epochs so distant our planet didn't even exist yet. Take the light from Andromeda, our closest galactic neighbor. By the time those photons land in your eye, they've been journeying for 2.5 million years. That means when you gaze at Andromeda tonight, you're seeing it as it looked when early humans were just beginning to walk upright. But the real magic happens when gravity steps in, twisting this ancient light like a funhouse mirror. Picture spacetime as a vast rubber sheet, with massive objects like galaxies creating deep dimples in its surface. When light from even more distant objects passes near these cosmic heavyweights, its path bends dramatically, sometimes splitting into multiple images or stretching into luminous arcs. This eerie effect, called gravitational lensing, turns the universe into a hall of mirrors where a single object can appear in several places at once, each version showing a slightly different moment in its history. One of the most stunning examples sits in the constellation Leo, where a massive galaxy cluster known as SDSS Joan 1148+53 acts as a natural telescope. Behind it, a far more distant galaxy is magnified and warped into a glowing ring, a so-called Einstein Ring, named for the physicist who first predicted this phenomenon. The light forming that ring began its journey when the universe was just 3 billion years old, making it a direct window into the cosmos' adolescence. What's truly mind-bending is how these lensed images don't just show us the past, they let us study it in impossible detail. When light takes different paths around a massive object, each version arrives at Earth at slightly different times, like staggered echoes of the same event. In 2014, astronomers witnessed a supernova nicknamed Gravitational appear 4 times around a galaxy cluster, with each image representing a different stage of the explosion. It was like watching a stellar death replay in slow motion across cosmic time. This time delay effect reveals something profound about the nature of reality itself. If we can see multiple versions of an event from different moments, does that mean the past still exists somewhere in the fabric of space-time? Modern physics suggests the answer might be yes, that what we perceive as the past isn't gone, but simply located elsewhere in the universe's vast space-time continuum. Every time we observe these gravitational mirages, we're not just studying the universe's history, we're touching the very structure of time, and the implications go beyond mere observation. By analyzing how much these light paths bend, scientists can map the invisible scaffolding of the cosmos, the mysterious dark matter that makes up most of the universe's mass. These cosmic reflections are more than pretty anomalies. They're tools letting us weigh the unseeable, measure the immeasurable, and ultimately understand how everything from galaxies to time itself came to be. The next time you hear about astronomers discovering some strange mirrored galaxy, remember, you're not just looking at a curiosity, you're witnessing the universe perform its most astonishing trick, turning light into a time machine. Einstein's vision of space-time bending under the weight of massive objects didn't just rewrite physics, it gave us a new way to see the universe. Gravitational lensing turns galaxy clusters into nature's telescopes, amplifying light from objects so faint they'd otherwise be invisible. But sometimes the cosmos takes this phenomenon and twists it into something even stranger. Take the Cheshire Cat galaxy group, where two massive elliptical galaxies seem to grin like the famous feline, their gravity stretching a background galaxy into a ghostly arc of light. It's not just a cosmic coincidence, it's a snapshot of space-time itself warping under immense mass, revealing how matter we can't even see shapes the paths of light. Then there's Hamilton's object, a bizarre double-lensed galaxy that appears split into 4 distinct images arranged in a cross. The light from this distant spiral has been bent around a foreground galaxy like water flowing around a stone, creating a perfect example of what astronomers call an Einstein Cross. Each of those 4 images is the same galaxy, but because the light took slightly different paths to reach us, they show it at slightly different moments in time. It's as if the universe pressed pause, rewind, and play simultaneously, giving us a multiplex view of cosmic history. But perhaps the most haunting lensed object lies in the constellation Fornax. Nicknamed the Ghost of Cassiopeia, this ethereal blue arc is the warped remains of a star-forming galaxy from when the universe was just 2 billion years old. Its light has been stretched and magnified by a foreground cluster so dramatically that astronomers can study individual star-forming regions within it, something normally impossible at such distances. This isn't just magnification, it's like the universe handed us a microscope tuned to the dawn of galaxy formation. What makes these lensed objects so valuable isn't just their strangeness, it's the secrets they reveal. When light splits into multiple images, each version carries unique information about the space it traveled through. By comparing them, scientists can map the distribution of dark matter in the lensing galaxy, measure the universe's expansion rate with precision, and even test whether Einstein's theory holds true across cosmic distances. Every distorted galaxy is a laboratory where the fundamental rules of reality are being probed, and sometimes the universe seems to play tricks on us. In 2018, astronomers spotted a distant star nicknamed Icarus that had been magnified over 2,000 times by a galaxy cluster, a record-breaking feat of natural lensing. But here's the twist: the star wasn't just magnified. As individual stars within the lensing cluster passed in front of it, they created micro-lensing events, causing Icarus to flicker like a candle in the cosmic wind. This serendipitous alignment gave us our first detailed look at a normal star 9 billion light-years away, proving that even the most fleeting cosmic alignments can become windows to the distant past. These lensed marvels do more than defy expectations, they redefine what's possible in astronomy. Without gravitational lenses, we'd be blind to some of the universe's earliest galaxies, missing crucial chapters in the story of how stars and planets came to be. They remind us that the cosmos isn't just expanding, it's alive with unseen forces sculpting the light that reaches us, turning empty space into a hall of mirrors where the past, present, and future collide. Every time we find another warped galaxy or multiplied quasar, we're not just discovering an oddity, we're witnessing space-time itself keeping a promise Einstein made over a century ago, that gravity doesn't just pull. It bends, distorts, and ultimately reveals. The Einstein Cross isn't just a cosmic curiosity, it's a masterpiece of gravitational artistry, a celestial illusion so precise it feels almost intentional. Nestled in the constellation Pegasus, this rare alignment features a brilliant quasar, a galaxy's supercharged heart, multiplied into 4 shimmering images around a foreground galaxy like petals on a flower. The quasar's light, emitted when the universe was barely a third of its current age, doesn't travel in a straight line to reach us. Instead, the gravity of the intervening galaxy warps spacetime so profoundly that the light forks into separate paths, each bending around the galaxy's edges before converging at our telescopes. The result, a single object frozen in 4 slightly different moments, a time lapse etched into the fabric of the cosmos. What makes the Einstein Cross so extraordinary isn't just its symmetry, it's the story each image tells. Because the light in each path travels a different distance, the 4 quasars aren't perfectly synchronized. One might show a flare in brightness while another lags behind, revealing changes that unfolded over thousands of years. It's as if the universe handed astronomers a control experiment, letting them study how quasars evolve by comparing these staggered snapshots. In 2019, scientists noticed something peculiar. One of the 4 images was growing brighter while the others remained steady. The culprit, a single star in the lensing galaxy passing through the quasar's line of sight, its gravity briefly magnifying the light like a cosmic magnifying glass. This fleeting event, called microlensing, offered a rare glimpse into the quasar's inner structure, proving even the tiniest players in the universe can shape how we see the distant past. But the deeper magic of the Einstein Cross lies in what it reveals about spacetime itself. Einstein's equations predicted such lensing was possible, but even he doubted we'd ever witness it. The odds of a quasar, galaxy, and Earth aligning so perfectly are astronomically low, yet here it is, a natural telescope crafted by gravity's invisible hand. By measuring the time delays between the quasar's images, astronomers can weigh the lensing galaxy with precision, mapping its dark matter halo in ways no other method allows. The cross becomes a scale measuring the unseen, and then there's the philosophical twist. If we're seeing the same quasar in 4 places, does that mean the quasar exists in 4 places? In a way, yes. Each image is real, each photon legitimate, just taking different routes through the universe's twisted geometry. This challenges our instinct that light travels in straight lines, reminding us that spacetime is more like a winding river than a static grid. The Einstein Cross doesn't just bend light, it bends our understanding of reality, proving that the universe doesn't just hold secrets, it mirrors them back to us if we know how to look. Perhaps most astonishing is how these cosmic mirages are becoming tools for discovery. In 2022, researchers used a distant Einstein Cross to test a bold idea. Could the universe's expansion rate vary in different directions? By comparing the quasar's lensed images with models, they found tantalizing hints that spacetime might stretch unevenly, a finding that, if confirmed, could rewrite cosmology. Every time we study this gravitational hall of mirrors, we're not just observing the universe, we're collaborating with it, letting its own distortions guide us to truths hidden in plain sight. The cross is more than an illusion. It's a conversation across time, with the universe whispering its oldest secrets through the very way it bends the light. Quasars are the universe's ultimate overachievers, celestial powerhouses so bright they outshine entire galaxies. At their core lies a supermassive black hole, but unlike the dormant giants lurking in most galactic centers, these are voracious beasts, swallowing stars and gas at staggering rates. As matter spirals inward, it heats up to millions of degrees, creating a swirling disk of white-hot plasma that blasts out enough light to be seen clear across the cosmos. Imagine a single object so luminous it could outshine 1 trillion suns, a beacon visible from over 13 billion light-years away. That's the raw power of a quasar, and it's precisely why they're such invaluable tools for peering into deep time. When quasars shine through the cosmic web, their light doesn't travel uninterrupted. It passes through galaxies, dark matter halos, and vast clouds of gas, each bending its path like a prism warping sunlight. Sometimes that distortion creates multiple images of the same quasar, split and magnified by gravitational lensing. Take the double quasar discovered in 1979. Two identical points of light later revealed to be mirrored reflections of a single object, its light bent around an unseen galaxy. These cosmic doppelgangers aren't just curiosities. By measuring how much the light splits and dims, astronomers can weigh the invisible dark matter warping its path, mapping structures we'd never see otherwise. But quasars do more than reveal hidden mass. They let us test the universe's expansion in real time. Because their light takes billions of years to reach us, subtle shifts in their brightness can signal changes in the cosmic landscape. In 2017, researchers used lensed quasars to clock the universe's expansion rate with unprecedented precision, comparing how quickly the space between galaxies stretched over eons. The results were startling. The universe seems to be expanding faster than our best models predict, a discrepancy that's still shaking up cosmology. It's as if these ancient lighthouses are sending us SOS signals from the past, hinting at physics we don't yet understand. What makes quasars truly transformative, though, is how they illuminate the universe's toddler years. The most distant ones we've spotted existed when the cosmos was less than 1 billion years old, yet they're already hosting black holes weighing billions of suns. That shouldn't be possible. Black holes need time to grow unless they started as inexplicably massive seeds. Their existence forces us to rethink how structures formed in the early universe, suggesting shortcuts or processes we've yet to uncover. Every lensed quasar is like finding a fossilized footprint from a creature we never knew existed, challenging our timelines of cosmic evolution. And then there's the eerie beauty of their reflections. Some quasars, lensed by galaxy clusters, stretch into shimmering arcs or appear as ghostly rings Einstein's predictions made visible. The quasar SDSS Joan 1029 plus 262, for instance, is warped into a near-perfect circle by a foreground galaxy, its light bent so completely it forms a halo around the lens. This isn't just gravity at work, it's spacetime itself curving into a natural telescope, magnifying details we'd never discern otherwise. Through these cosmic lenses, we've spotted quasars flickering as stars pass in front of them, mapped the clumpy distribution of dark matter, and even caught glimpses of the faint gas clouds that birthed the first galaxies. Quasars remind us that the universe's past isn't locked away. It's written in light, twisted and magnified by the very fabric of reality, waiting for us to decode it. They're not just relics, they're active participants in our quest to understand deep time. They're distorted reflections serving as both map and compass in the vastness of cosmic history. The next time you hear about astronomers spotting a multiply-imaged quasar, remember, you're not just looking at a black hole's glare, you're seeing the universe fold time itself, offering us a front-row seat to its most ancient spectacles. Galaxy clusters are the universe's ultimate magnifying glasses, colossal cities of hundreds or even thousands of galaxies bound together by gravity so intense it warps the very fabric of space around them. Picture dropping a bowling ball onto a trampoline, watching the fabric dip dramatically beneath its weight. Now imagine that distortion isn't just bending a surface, it's twisting the paths of light itself. That's what happens when light from a distant galaxy passes near a massive cluster. Instead of traveling straight, it curves around this gravitational well, stretching and magnifying like an image seen through the bottom of a wineglass. The Hubble Space Telescope's Frontier Fields project took full advantage of this cosmic quirk, turning 6 massive galaxy clusters into natural telescopes. One of them, Able 1689, is so massive that it magnifies galaxies behind it by up to 30 times. Through its lens, Hubble spotted galaxies so faint they'd otherwise be invisible flickering candles from when the universe was just 500 million years old. These aren't just distant objects, they're snapshots of the cosmic dawn, the moment the first stars pierced the darkness of the early universe. But the real magic happens in the details. When a cluster lenses a background galaxy, it doesn't just make it brighter, it often distorts it into surreal shapes. Some appear as luminous arcs, like smeared brushstrokes across the sky. Others split into multiple copies, a single galaxy mirrored in perfect symmetry around the cluster's heart. Take Max J0717.5 plus 3745, a cluster so effective at lensing that it's nicknamed the Cosmic Horseshoe. Behind it lies a galaxy stretched into a near-perfect ring, its light bent so completely it forms a glowing halo around the cluster. These warped images aren't just pretty anomalies, they're gold mines of information. By analyzing how much the light bends, astronomers can map the cluster's invisible dark matter, the mysterious substance making up most of its mass. It's like watching wind bend the flames of a candle to deduce the shape of an unseen hand. In 2018, one lensed galaxy revealed dark matter's distribution in unprecedented detail, showing it wasn't smoothly spread but clumped in ways that challenged existing theories. Time behaves strangely around these cosmic lenses too, because light takes different paths around the cluster. Some images arrive later than others, like echoes of the same event bouncing off distant walls. In 2021, astronomers used this effect to witness a supernova explosion replay itself 3 times over several years, each appearance showing a different moment in the star's death throes. It was as if the universe had pressed rewind, letting them study the same cataclysm from multiple angles. What makes galaxy clusters so extraordinary is how they transform the cosmos into an interactive museum. Without them, those first galaxies would remain hidden, their light too feeble to pierce the vastness of space. But thanks to gravity's magnifying power, we're not just observers of cosmic history. We're detectives using these natural telescopes to uncover secrets the universe never meant to reveal so easily. Every distorted arc, every mirrored galaxy, is a whispered clue about how everything, from the tiniest particles to the grandest clusters, came to be. In 1995, astronomers pointed the Hubble Space Telescope at what looked like nothing, a patch of sky no bigger than a grain of sand held at arm's length, seemingly empty to every other telescope. For 10 straight days, Hubble collected every whisper of light it could, and when the image finally emerged, it shattered our understanding of the cosmos. What appeared to be void was actually a bustling metropolis of galaxies, over 3,000 of them crammed into a sliver of darkness. The Hubble Deep Field wasn't just a photograph. It was a time machine capturing light that had been traveling for up to 12 billion years, showing us galaxies as they existed when the universe was in its chaotic infancy. What makes the deep field so extraordinary isn't just the sheer number of galaxies, it's their variety. Some are orderly spirals, their arms pinwheeling with newborn stars. Others are misshapen blobs caught in the act of violent collisions, their structures distorted by gravitational tug-of-wars. A few are nothing more than faint smudges, galaxies so young they're still assembling themselves from the primordial gas of the early universe. Each one is frozen in a specific moment, like insects trapped in amber, offering a direct line to epochs long gone. But here's the haunting part: many of those galaxies no longer exist. Over billions of years, some have merged into larger structures, their stars scattered into new configurations. Others have faded into obscurity, their fuel for star formation exhausted, leaving behind ghostly husks. When we look at the deep field, we're not just seeing the past, we're seeing a graveyard of cosmic eras, a reminder that even galaxies have life cycles. The genius of the deep field lies in its simplicity. By staring at nothing, Hubble revealed the universe's deepest truth: there is no such thing as empty space. Every direction we look is stacked with layers of time, light from different eras overlapping like pages in a book. Later deep field images, like the Hubble Ultra Deep Field and the Extreme Deep Field, pushed even further, uncovering galaxies from when the universe was just 400 million years old, a time when the first stars were still cutting through the darkness. These images do more than dazzle, they rewrite cosmic history. Before Hubble, we had no idea the early universe was so crowded, or that galaxies formed so quickly after the Big Bang. The deep field forced us to confront how little we knew about galaxy evolution, sparking new theories about how these colossal structures grow and change. It also revealed something profound about our place in the universe. In that empty patch of sky, every speck of light was an entire galaxy, each home to billions of stars. The sheer scale is humbling, a reminder that our Milky Way is just one voice in a cosmic choir. Perhaps the most astonishing lesson of the deep field is how it turns light into a historian. The photons hitting Hubble's mirror had been traveling since before Earth existed, carrying stories of cosmic dawn. Some passed through clouds of primordial gas, their wavelengths subtly altered by the chemistry of the early universe. Others were bent by invisible dark matter, their paths twisted like clues in a detective story. Every distortion, every shift in color, is a piece of evidence waiting to be decoded. The deep field isn't just a snapshot, it's a mirror. When we peer into its depths, we're not just observing distant galaxies, we're witnessing the universe's relentless evolution, watching as it builds, destroys, and rebuilds itself across the eon. It's a reminder that the night sky isn't a static painting. It's a living, breathing chronicle, and every time we train our telescopes on the darkness, we're turning another page in the story of everything. Supernova Wildest should have been a one-time cosmic spectacle, a brilliant stellar explosion fading into darkness like countless others before it, but the universe had other plans. When this dying star's light reached the galaxy cluster Max Joan 1146 plus 2238, it didn't just pass through. The cluster's immense gravity twisted spacetime so severely that the supernova's light forked into multiple paths, like beams splitting through a prism. The result, a single cataclysm replaying across the sky, with each image revealing a different chapter of the star's death throes. The first 4 appearances of Wildest arrived in late 2014, arranged in a striking cross-shaped pattern around the cluster's core, a celestial time-lapse created purely by the universe's warped geometry. Each image showed the supernova at slightly different phases, separated by days or weeks as the light traversed varying distances around the cluster. But the real shock came when astronomers crunched the numbers. Their models predicted a 5th image would emerge over a year later, delayed by an even longer detour through the cosmic labyrinth. In December 2015, right on schedule, Wildest's final encore flickered to life, a ghostly reappearance confirming that gravity doesn't just bend light. It bends time itself. What makes Wildest extraordinary isn't just its multiplied images, It's what they revealed about the invisible scaffolding of the cosmos. By precisely measuring the time delays between each appearance, astronomers could map the distribution of dark matter within the cluster with unprecedented accuracy. The supernova's staggered arrivals acted like sonar pings echoing through unseen structures, exposing how dark matter clumps and spreads on scales smaller than ever observed. Some models even suggested the presence of rogue dark matter substructures, invisible fragments drifting between galaxies like cosmic fog banks that standard telescopes could never detect. This cosmic rerun also gave scientists a rare chance to test Einstein's theory under extreme conditions. The timing of each Riefstahl image matched his predictions to within 10%, an astonishing feat considering the complex interplay of gravity involved. But there were subtle discrepancies, tiny mismatches that might hint at physics beyond Einstein's framework, perhaps tied to dark energy's mysterious influence on cosmic expansion. It's as if the universe handed researchers a controlled experiment, with the supernova serving as both test subject and timer. Beyond the physics, Riefstahl offers something more profound, a glimpse into astronomy's future. By analyzing such lensed supernovas, we're essentially learning to predict the past, anticipating when and where ancient stellar explosions will reappear in our skies. Upcoming telescopes like the Vera Rubin Observatory could detect dozens of these time-delayed echoes, transforming them into standard tools for probing dark matter and cosmic expansion. Imagine knowing a supernova will brighten a specific galaxy next Tuesday, 10 billion years after it actually happened. That's the surreal promise of gravitational lensing, not just observing history but scheduling repeat viewings. Supernova Riefstahl's greatest lesson might be about perspective. We're accustomed to thinking of light years as vast distances, but they're also time-stamps, markers of how long a photon journeyed before reaching us. Lensing scrambles that linear narrative, proving that in a curved universe, the past isn't locked away. It's folded into the present, waiting for the right gravitational conditions to reveal itself again. Every time we spot another lensed supernova, we're not just seeing a star's death. We're witnessing spacetime's memory at work, replaying the cosmos' most violent moments like a skipping record, each echo revealing secrets the universe thought it had erased. Time bends around massive galaxies like water flowing around a boulder, sometimes slowing to a trickle, sometimes rushing ahead. When light from a distant quasar splits into multiple paths around a gravitational lens, each version races toward Earth along a different cosmic obstacle course. One beam might skim close to the lensing galaxy, feeling its full gravitational pull, while another takes a wider, less impeded route. The result, a single event, a quasar's flare, a supernova's explosion reaching us in staggered installments, like chapters of a story arriving out of order. Take the quasar JWST 1055 plus 421, whose light divides into 4 images around a foreground galaxy. In 2013, astronomers noticed something peculiar. One image brightened months before the others, revealing the quasar's flickering activity in delayed sequences. By tracking these time lags, researchers could reconstruct the quasar's history in exquisite detail, watching how its outbursts evolved over years as the light trickled in via different routes. But more crucially, those delays acted as cosmic stopwatches, letting scientists measure the gravitational pull of the lensing galaxy with precision. The longer the delay between images, the more space-time curved along that light's path, a direct probe of invisible mass. These delays aren't just minor curiosities. In the case of the double quasar QSO 9597 plus 5614, the two images arrive nearly 420 days apart. That gap isn't random. It's a fingerprint of the lensing galaxy's dark matter halo, revealing how this invisible substance clusters around galaxies in ways that defy simple predictions. When light takes the scenic route, it doesn't just tell us about the source. It maps the unseen topography of space-time itself. Perhaps the most astonishing application of time delays is measuring the Hubble constant, the rate at which the universe expands. By comparing how long lensed light takes to reach us with models of the lensing galaxy's mass, astronomers can calculate how much the universe stretched during that light's journey. It's like measuring the growth of a tree by comparing rings in its bark, except the tree is all of space-time, and the rings are echoes of light from a quasar. Recent results have sparked controversy, with some lensed systems suggesting a faster expansion rate than other methods. This discrepancy might hint at new physics. Perhaps dark energy's strength changes over time, or our understanding of gravity needs revising. But time delays also reveal the universe's whimsical side. In 2021, astronomers watched a supernova named Requiem appear 3 times around a galaxy cluster, with the final image predicted to show up. Wait for it, around the year 2377. That's right, we're seeing spoilers for a stellar explosion whose last act won't be visible for another 3 centuries. It's as if the universe is teasing us with fragments of a story we won't live to see completed. What makes these cosmic echoes so powerful is their versatility. They serve as scales to weigh dark matter, clocks to measure cosmic expansion, and even telescopes to magnify the distant universe. By studying how lensed images brighten and fade out of sync, we're not just observing the cosmos, we're engaging in a form of gravitational forensics, reconstructing events we can't witness directly by reading the wrinkles they leave in spacetime. Every delayed photon is a messenger from 2 places at once: the distant object that emitted it and the invisible mass that bent its path. Together, they're rewriting the rules of cosmic detective work, proving that sometimes the best way to see the universe clearly is to wait for its reflections to catch up. Dark matter doesn't glow, absorb, or reflect light, yet it's everywhere, sculpting the cosmos in ways we're only beginning to understand. When galaxies cluster together, their gravity should be far too weak to explain how fast they spin or how violently they collide. Something invisible, something massive, must be holding them together. That's where gravitational lensing becomes our most powerful tool. As light from distant galaxies passes through these unseen halos of dark matter, it doesn't just bend, it twists into telltale shapes, revealing the fingerprints of an otherwise hidden universe. Take the Bullet Cluster, one of the most dramatic examples of dark matter's ghostly handiwork. When 2 galaxy clusters collided at millions of miles per hour, their hot gas clouds, the only part we can see directly, slammed together and stalled like smoke caught in a cosmic wind. But the lensing effect revealed something astonishing. The cluster's gravity didn't follow the gas. Instead, it stayed with invisible masses that had sailed right through the collision, unaffected. The only explanation: dark matter, interacting so weakly with itself and everything else that it passed through the chaos like a phantom. But not all dark matter behaves so predictably. Some lensed galaxies appear more distorted than our models expect, as if their dark matter halos are clumpier or more concentrated than theory allows. In 2018, observations of a lensed galaxy nicknamed the Dragonfly showed arcs of light that couldn't be explained by smooth, evenly distributed dark matter. Instead, they hinted at tiny, dense knots of its substructures too small to form under standard physics. Could dark matter be more complex than we thought? Might it interact with itself in ways we haven't yet imagined? Every warped galaxy image is a new piece of the puzzle, forcing us to reconsider what this mysterious substance truly is. The most tantalizing clues come from Einstein rings, those perfect circles of light formed when a distant galaxy aligns precisely behind a massive lens. The symmetry of these rings depends entirely on how dark matter is arranged, and some rings aren't perfectly round. Their slight asymmetries suggest dark matter isn't just a featureless fog. It might have texture, subtle variations in density that trace the cosmic web's filamentary structure. By mapping these imperfections, astronomers are essentially drawing blueprints of the universe's invisible skeleton, showing how dark matter channels galaxies into vast, interconnected networks. And sometimes lensing reveals outright anomalies. In 2020, researchers studying a galaxy cluster found a lensed arc that seemed to defy gravity's rules. Its distortion implied the presence of a massive object, yet there was nothing visible there. Dubbed a dark clump, this ghostly concentration of mass could be a rogue fragment of dark matter, untethered to any galaxy, drifting through space like an iceberg in the cosmic ocean. If confirmed, such clumps would challenge our assumption that dark matter always clusters around visible matter, suggesting it might form structures all on its own. What makes these discoveries so exhilarating is how they turn the universe's distortions into a laboratory. We can't capture dark matter in a detector yet, but we don't need to. Its gravity writes its signature in the light of everything behind it, leaving trails we're learning to follow. With next-generation telescopes like the Vera Rubin Observatory set to discover millions more lensed galaxies, we're on the verge of mapping dark matter in unprecedented detail, tracing its whispers across billions of light years. The universe's mirrors aren't just reflecting light, they're reflecting the invisible, showing us a side of reality we'd never glimpse otherwise. And with every distorted image, every warped arc, we're one step closer to answering the biggest question of all. What is the universe really made of? The James Webb Space Telescope isn't just a technological marvel. It's a time machine with infrared eyes, peeling back layers of cosmic history we never thought we'd see. Since its launch in 2021, JWST has been capturing light so ancient it was emitted when the universe was a mere 5% of its current age. But here's the twist. Some of its most breathtaking discoveries aren't just distant galaxies, they're reflections of those galaxies, warped and magnified by gravitational lenses into surreal, elongated arcs. These cosmic mirages are like messages in a bottle, sent from the universe's infancy and delivered to us via the universe's own funhouse mirrors. One of JWST's earliest stunners was a galaxy nicknamed Glass Z13, whose light traveled for an astonishing 13.4 billion years before reaching us. But without the helping hand of a foreground galaxy cluster bending and amplifying its faint glow, we'd never have spotted it. This isn't just a record breaker, it's a paradox. The galaxy appears too massive, too mature for its age, cramming hundreds of billions of stars into a structure that shouldn't have had time to form so soon after the Big Bang. Either our models of galaxy growth are missing something fundamental, or the early universe worked in ways we're only beginning to grasp. Then there's the Sunrise Arc, a galaxy stretched by gravitational lensing into a hair-thin crescent 12 times longer than our Milky Way. JWST razor-sharp vision revealed something unprecedented within it. Individual star-forming regions no bigger than 1,000 light-years across, pockets of furious stellar birth from when the universe was barely 300 million years old. These aren't just baby galaxies, they're galaxies caught in the act of being born, their construction processes frozen in time by the very lensing effect that makes them visible. The detail is so crisp, it's like finding a high-resolution photo tucked inside a 13th-century manuscript. but JWST real power lies in its ability to decode the chemistry of these ancient reflections. By splitting their light into rainbows, a technique called spectroscopy, the telescope has detected heavy elements like oxygen and carbon in galaxies that existed just 500 million years after the Big Bang. That's a cosmic heartbeat, far too soon for these elements to have formed through normal stellar processes alone. The implication: the first stars must have lived fast and died violently, seeding the cosmos with the raw materials for planets and life far earlier than anyone predicted. Perhaps most mind-bending are JWST glimpses of protoclusters, dense knots of galaxies in the process of assembling into the massive city-like structures we see today. One such group, magnified by the lensing cluster SMACS 0723, shows a dozen tiny galaxies packed into a space just 3 times the size of the Milky Way. They're not yet colliding, they're dancing in slow motion, drawn together by gravity's invisible threads. Watching these cosmic embryos is like stumbling upon the blueprints for modern galaxy clusters, revealing how the universe's largest structures grew from such humble beginnings. Every JWST image of a lensed galaxy is a double revelation. First, it shows us an object from the dawn of time. Second, it exposes the hidden hand of dark matter shaping that light's path, turning the cosmos into a natural particle detector. When the telescope spots a galaxy warped into a perfect Einstein ring, it's not just capturing a pretty picture, it's weighing the invisible scaffold that holds the universe together. With each new observation, JWST isn't just rewriting the story of the early cosmos. It's proving that the universe's reflections are its most honest mirrors, revealing truths about our origins that direct light could never show. The irony is delicious. To see the universe at its youngest, we rely on the very same gravitational tricks that warp space-time. Without these natural telescopes, the first galaxies would remain invisible, their light stretched and dimmed by cosmic expansion into near nothingness. But thanks to JWST infrared eyes and gravity's magnifying glass, we're not just peering into deep time, we're holding a conversation with it, asking questions the universe has been waiting 13 billion years to answer. Among the most mysterious candidates for gravitational lenses are the hypothetical primordial black holes, cosmic relics that might have formed in the chaotic first moments after the Big Bang. Unlike the black holes we know today, born from collapsing stars, these would have condensed directly from the universe's seething infancy, when densities were so extreme that random fluctuations could collapse into darkness. Imagine pockets of space so dense they punched straight through the fabric of reality, leaving behind black holes no heavier than a mountain yet as ancient as time itself. If they exist, these primordial black holes could be drifting through the cosmos right now, invisible but for the way they bend the light of distant stars like hidden lenses floating in the void. The hunt for these elusive objects hinges on a subtle cosmic quirk, microlensing. When a primordial black hole passes in front of a distant star, its gravity briefly magnifies the star's light, causing it to flare unpredictably before fading back to normal. Astronomers have catalogued thousands of these fleeting events, most caused by ordinary stars or planets, but a handful defy explanation. Their lensing effects too sharp, too quick, matching the profile of something far smaller and denser than any known celestial body. Could these be the fingerprints of primordial black holes, flitting through the galaxy like cosmic ghosts? What makes this possibility so tantalizing is the window it could open into the universe's first microseconds. Primordial black holes wouldn't just be relics, they'd be time capsules, preserving clues about the conditions of the Big Bang that no other object can. Their very existence would imply that the early universe was lumpier than our models predict, with wild density variations that collapsed into black holes before the first atoms even formed. Some theories suggest these black holes could solve one of cosmology's biggest puzzles, the nature of dark matter. If they're abundant enough, they might account for the invisible mass holding galaxies together, replacing exotic particles with something even stranger, black holes forged in the birth of spacetime itself. The search is pushing telescopes to their limits. Projects like the Subaru Hyper Subprime Cam survey scan millions of stars nightly, looking for the telltale flickers of microlensing. In 2017, one such event, dubbed MOA 2011 BLG 191, caught researchers' attention. The lensing object was too small to be a star, too heavy to be a planet, and it left no heat signature. The best fit, a black hole roughly the mass of the Moon. While not definitive proof, it's the kind of anomaly that keeps the primordial black hole hypothesis alive. But the real breakthrough could come from gravitational wave astronomy. If two primordial black holes were to collide, the ripples in spacetime they'd create would carry a unique signature, a high-pitched chirp distinct from the mergers of stellar black holes. LIGO and Virgo detectors are listening closely, and some speculate that certain detected events might already fit the bill. Each unexplained signal fuels the debate, turning abstract theory into a tangible cosmic treasure hunt. Discovering primordial black holes would do more than add a new class of object to the cosmos. It would rewrite the first chapter of universal history, proving that black holes weren't just endpoints of stellar lives. They were there at the beginning, silent witnesses to the dawn of everything. Their lensed whispers, if we can decode them, might reveal secrets no telescope could ever see directly. How spacetime behaved under conditions so extreme they make supernovas look tame. They're not just lenses, they're messages from a time before time, waiting for us to read the light they've bent across the ages. What if the reflections we see in deep time aren't just echoes of our own universe, but glimpses of others? The multiverse hypothesis, once relegated to science fiction, is now a serious topic in cosmology, and gravitational lensing might hold the key to testing it. Imagine light from a distant quasar bending around a galaxy cluster, only instead of following the expected path, it carries subtle anomalies, distortions that can't be explained by the visible mass alone. Some theorists suggest these quirks could be fingerprints of parallel universes brushing against ours, their gravity leaking through unseen dimensions and warping spacetime in ways we're only beginning to imagine. The math behind this idea is as elegant as it is mind-bending. In certain multiverse models, neighboring universes could exert gravitational pull on ours, creating faint imprints in the way light bends around massive objects. These distortions would be incredibly subtle, like detecting a whisper in a hurricane, but next-generation telescopes like the Vera Rubin Observatory might be sensitive enough to spot them. One tantalizing clue came from the Planck satellite's map of the cosmic microwave background, which revealed unexplained cold spots and asymmetries. Could these be cosmic bruises, places where another universe collided with ours in the distant past? Skeptics argue these anomalies could have mundane explanations, instrumental noise, statistical flukes, or gaps in our understanding of dark matter. But the sheer scale of gravitational lensing offers a unique testing ground. If multiple lensed images of the same object show inconsistent distortions, or if light appears to bend where no known mass exists, these could be the breadcrumbs leading to a radical conclusion, that our universe is just one page in an infinite cosmic library. Even if the multiverse remains unproven, the pursuit reveals something profound about how deep time reshapes our curiosity. The same lensing effects that let us peer back to the universe's infancy might also let us peer sideways into realms where physics operates differently, where constants like gravity or the speed of light aren't constants at all. It's a reminder that the universe's reflections aren't just about what was. They're about what could be, pushing us to question not just the nature of reality, but the nature of possibility itself. And that's the real power of these cosmic mirrors. Whether they ultimately reveal parallel universes or not, they force us to think bigger. If space-time can bend light into loops and arcs, why couldn't it bend into bridges between worlds? Every anomalous lensed image, every unexplained warp in starlight, is an invitation to wonder. Are we reading the universe's diary, or just one sentence in a story too vast to comprehend? The answer, like the light from those distant galaxies, might still be on its way to us. The cosmic microwave background isn't just light, it's the universe's baby picture, a faded photograph from when everything was just 380,000 years old. Picture the cosmos at that moment, hot, dense, and glowing like the inside of a star, with no galaxies, no planets, not even atoms as we know them. Just a seething plasma of particles and energy, too chaotic for light to travel more than a fraction of an inch before scattering. Then, in a cosmic instant, everything changed. The universe cooled just enough for atoms to form, freeing light to stream across space for the first time. That primordial flash, stretched by 14 billion years of expansion, still reaches us today as a faint microwave whisper, colder than the void between stars. What makes the CMB extraordinary isn't just its age, it's the story written in its imperfections. To the naked eye, this afterglow looks perfectly smooth, a uniform haze across the sky. But sensitive telescopes like Planck and WMAP have revealed something astonishing: tiny variations in temperature, fluctuations no larger than 1 part in 100,000. These speckles of warmth and cold aren't random. They're cosmic hieroglyphs encoding the seeds of every structure we see today. A slightly denser patch here became a galaxy cluster. A cooler spot there evolved into a vast cosmic void. The universe's entire blueprint is hidden in these patterns, waiting to be decoded. Scientists read these fluctuations like a forensic analyst studies fingerprints. The distribution of hot and cold spots reveals the universe's composition down to the decimal: 5% ordinary matter, 27% dark matter, and 68% dark energy, numbers that define everything from the fate of galaxies to the ultimate destiny of spacetime itself. The CMB even carries echoes of the universe's violent birth. In 2014, researchers claimed to detect faint swirls in the CMB's polarization, a potential smoking gun for cosmic inflation. The theory that the universe underwent an exponential growth spurt in its first trillionth of a second. Though controversial, the finding hints that the CMB might hold clues to physics far beyond our current understanding. But the real magic lies in how this ancient light interacts with the cosmos. As CMB photons travel toward us, they don't just passively record the universe's expansion. They actively encounter it. Some pass through galaxy clusters so massive they warp spacetime, their gravity bending the light's path and subtly altering its temperature. This effect, called the Sunyaev-Zeldovich phenomenon, lets astronomers map dark matter in 3 dimensions, turning the CMB into a backlight that illuminates the invisible scaffolding of the universe. Other photons scatter off electrons in galaxy clusters, leaving faint shadows that reveal the locations of these cosmic metropolises billions of light years away. The CMB is more than a relic. It's a mirror reflecting the universe at every stage of its evolution. When we observe its fluctuations, we're seeing the first gravitational waves, ripples in spacetime from the Big Bang itself. When we track its distortions, we're watching dark energy push galaxies apart over eons. And when we measure its temperature with ever greater precision, we're essentially taking the universe's pulse, checking for deviations that might hint at exotic physics or even parallel universes. This primordial glow isn't just background noise. It's the foundation of everything, a living record that connects the first moments of creation to the stars above us tonight. Perhaps the most humbling thought is this: the CMB doesn't just surround us, it passes through us. Hundreds of those ancient photons zip through your body every second, unchanged since the universe was a swirling plasma. They're the closest thing we have to a time machine, carrying unfiltered messages from an era before time had meaning. And with next-generation telescopes like the Simons Observatory poised to study it in unprecedented detail, the CMB's whispers may soon become a shout, revealing secrets about the universe's birth that we've only begun to imagine. Long before galaxies or stars existed, the universe was a roiling sea of plasma so dense that sound waves could travel through it at half the speed of light. These weren't ordinary sound waves, they were pressure pulses rippling through the newborn cosmos, pushed outward by radiation's fierce pressure and pulled back inward by gravity's relentless tug. For nearly 400,000 years, this cosmic tug-of-war created a rhythmic pattern of compression and rarefaction, like the vibrations of a colossal bell ringing across the infant universe. Then, in an instant, everything froze. When the cosmos cooled enough for atoms to form, the music stopped, but the echoes remained imprinted forever in the distribution of matter like fossilized ripples in a pond. Today, we call these echoes baryon acoustic oscillations, and they're one of the most powerful tools we have for measuring the universe's expansion. What makes BAOs so extraordinary is their scale. Those primordial sound waves traveled about 500,000 light-years before the universe cooled and locked them in place, a distance that now stretches to nearly 500 million light-years due to cosmic expansion. This means the large-scale structure of the universe isn't random. Galaxies are slightly more likely to be found at a specific distance from one another, a relic of those ancient pressure waves. Picture throwing pebbles into a pond and watching the ripples spread outward. Now imagine those ripples freezing mid-motion, leaving permanent ridges where the wave crests had been. That's essentially what happened to the universe, with galaxy clusters tracing the peaks of those frozen sound waves billions of years later. Astronomers map these patterns using galaxy surveys so vast they defy comprehension. Projects like the Sloan Digital Sky Survey have catalogued millions of galaxies, revealing a subtle but unmistakable preference for pairs separated by that 500 million light-year scale. It's as if the universe left us a ruler etched into the fabric of space itself, a ruler that grows as the cosmos expands. By measuring how much that standard distance has stretched over time, scientists can track the universe's expansion history with precision, uncovering how dark energy's repulsive force has accelerated it over the last 5 billion years. But BAOs do more than measure expansion, they're time capsules from the universe's first moments. The exact pattern of those sound waves depends on the primordial mix of ordinary matter, dark matter, and dark energy, letting astronomers weigh the cosmos's ingredients with astonishing accuracy. When combined with cosmic microwave background data, BAOs have helped pin down the universe's age to 13.8 billion years, its flat geometry, and even the timing of when dark energy began dominating gravity's pull. They're like cosmic tree rings, each oscillation a growth marker in the universe's life story. Perhaps most astonishing is how these frozen sound waves connect the largest and smallest scales of reality. The same quantum fluctuations that spawned BAOs also seeded all cosmic structure, meaning the galaxies we see today, grew from microscopic wrinkles in space-time amplified by those primordial vibrations. Every star, every planet, every atom in your body exists because of pressure waves that course through a plasma younger than 1,000,000 years. The universe didn't just leave us a ruler, it left us a creation myth written in the positions of galaxies, a testament to how deeply interconnected everything truly is. And the story isn't over. Next-generation telescopes like the Dark Energy Spectroscopic Instrument are mapping BAOs in 3 dimensions, using them to probe dark energy's nature with unprecedented precision. Some theories suggest dark energy's strength might change over time, a possibility these cosmic sound waves could confirm or refute. Every new galaxy survey is like adding another frame to a time-lapse of the universe's expansion, letting us watch as those ancient ripples stretch and distort under the influence of forces we're only beginning to understand. The universe didn't just sing a song at its birth, it wrote the sheet music into the very fabric of space, and we're only now learning how to read it. Light doesn't just travel across the universe, it battles against the expanding fabric of space itself. Every photon emitted by a distant galaxy is engaged in a cosmic tug of war, fighting to maintain its energy as the very space it moves through stretches like taffy. This phenomenon, called cosmological redshift, isn't just a subtle color change, it's an irreversible transformation. Imagine shouting into a storm where the wind carries your voice away, stretching each syllable until it becomes inaudible. That's what happens to light over cosmic distances, with the expansion of space pulling its wavelengths longer and redder until some signals fade beyond recognition. The consequences are profound. Right now, we can observe galaxies whose light has traveled for over 13 billion years, but future astronomers won't be so lucky. As the universe accelerates its expansion due to dark energy, galaxies beyond our local group will eventually redshift to the point where their light becomes undetectable. The photons that today reveal majestic spirals and colliding clusters will tomorrow stretch into radio waves, then fade into nothingness. In 1 trillion years, the night sky will be nearly empty to any observers in the Milky Way, with all other galaxies having vanished beyond an invisible horizon. The cosmic reflections we take for granted, Einstein rings, lensed supernova, quasars, are temporary gifts, visible only during this brief window when the universe is old enough to be transparent but young enough that light can still reach us. This isn't just about losing pretty pictures. Each redshifted photon carries irreplaceable information. When the light from distant supernova stretches too far, we'll lose our ability to measure cosmic expansion directly. When lensed galaxies fade, so does our window into dark matter's distribution. It's as if the universe is slowly closing history books we've only begun to read. The James Webb Space Telescope's stunning infrared views of early galaxies. Those targets will eventually redshift beyond even infrared detection, their stories lost to future civilizations. Yet there's a strange beauty in this cosmic forgetting. The same expansion that erases distant galaxies also creates isolated islands of matter regions like our local group where gravity overcomes dark energy's push. In the far future, these bound structures may be all that remains visible, their stars burning out one by one as the cosmos grows cold and dark. But for now, we're privileged to witness an extraordinary era when light from across time still reaches us, when reflections from the universe's youth haven't yet faded into the expanding night. Every warped galaxy image, every lensed quasar, is like catching fireflies in a jar, brief, flickering glimpses of a cosmos that won't always be so generous with its light. This ephemeral quality makes our current observations priceless. When astronomers measure redshifted light from galaxy clusters, they're not just studying the past, they're racing against the future, documenting cosmic history before it slips away. The universe's reflections are more than scientific data, they're postcards from a disappearing world, reminders that even the cosmos keeps secrets it won't reveal forever. Our ability to see deep time is a temporary miracle, one that future civilizations might never experience. So when you look up at the stars tonight, remember, you're not just seeing light. You're catching it just in time. The universe's grand tapestry, its galaxy clusters, sprawling filaments, and vast cosmic voids was woven from threads so delicate they defy comprehension. In the first trillionth of a second after the Big Bang, space itself crackled with quantum fluctuations, microscopic ripples where particles flickered in and out of existence like static on a cosmic radio. These weren't just fleeting anomalies. When inflation, the universe's explosive growth spurt, stretched spacetime exponentially, it magnified those quantum tremors from subatomic scales to cosmic proportions, etching them permanently into the fabric of reality. Today, those same ripples define where galaxies cluster and where darkness reigns, their fingerprints visible in every warped reflection of gravitationally lensed light. Consider the cosmic microwave background, that ancient afterglow from the universe's infancy. Its temperature variations, tiny patches slightly hotter or colder than average, are direct descendants of those quantum fluctuations. Where matter was marginally denser, gravity had a stronger grip, pulling in gas that would eventually ignite as stars. Where it was thinner, voids emerged. This cosmic connection between quantum mechanics and galactic architecture is so precise that scientists can simulate the universe's evolution from these initial conditions, and the results match the sprawling web of galaxies we observe. Without those primordial irregularities, the cosmos would be as smooth as glass, devoid of the structure that bends light into the reflections we study. Gravitational lensing acts as a cosmic magnifying glass for these ancient imperfections. When light from distant galaxies bends around massive clusters, it doesn't just reveal the cluster's mass, it exposes the legacy of those quantum seeds. The lensed arcs and multiple images we see are the end result of a chain reaction that began with fluctuations smaller than an atom. Even the distribution of dark matter, invisible except for its gravitational pull, traces back to these quantum origins. The clumps and filaments we infer from lensing distortions aren't random. They're the grown-up versions of quantum ripples stretched across billions of light years. One of the most striking examples lies in the cosmic web, the network of galaxy filaments connecting the universe like neurons in a vast brain. Simulations based on quantum fluctuations predict this web's structure with eerie accuracy, and lensing observations confirm it. The cluster Abell 1689, for instance, doesn't just magnify background galaxies, it stretches them along the invisible threads of dark matter that grew from those initial quantum bumps. The same physics governing electrons in a lab now explains why some patches of sky gleam with lensed galaxies while others yawn as empty voids. This marriage of quantum mechanics and cosmology reshapes how we see deep time. When astronomers analyze a lensed quasar's multiple images, they're not just measuring gravity's pull, they're glimpsing the aftermath of quantum events so old that stars hadn't yet formed. The time delays between those images, some arriving years apart, encode the growth of structures born from subatomic tremors. It's as if the universe took quantum uncertainty and froze it into celestial architecture, then used that architecture to bend light back on itself in an endless hall of mirrors. Yet mysteries remain. Why did certain quantum fluctuations prevail over others? Could alternate versions of our universe with different initial fluctuations look radically different? Some theories suggest these variations might even hint at multiverses, each with its own unique pattern of cosmic reflections. What's undeniable is that without quantum physics' delicate chaos, the universe would lack the texture that makes lensing and, by extension, our view of deep time possible. The next time you see an Einstein ring or a warped galaxy, remember, you're not just seeing gravity's handiwork, you're witnessing quantum mechanics painted across the cosmos, its microscopic brushstrokes magnified into the grandest art gallery imaginable. Simulating the universe's reflections isn't just science, it's cosmic time travel on a supercomputer. Imagine reconstructing the entire history of space-time, from the Big Bang's fiery aftermath to the intricate web of galaxies we see today, all inside a machine. That's exactly what projects like the Millennium Simulation accomplish, using billions of virtual particles to recreate how dark matter clumps together, how galaxies collide, and most crucially, how light bends around these cosmic structures. These aren't just animations, they're precision-engineered universes, running physics equations at scales so vast they make planetary orbits look simple. And when astronomers plug in the rules of gravity, dark energy, and lensing, something magical happens. Virtual telescopes inside the simulation start capturing eerily accurate copies of real Einstein rings, warped arcs, and multiplied quasars. The real power lies in the details. When light bends around a simulated galaxy cluster, it doesn't just follow smooth curves. It reveals the gritty texture of dark matter's invisible scaffolding. Supercomputers like NASA's Pleiades can track how tiny fluctuations in the early universe snowballed into the dense knots of matter that distort modern-day lensed images. One groundbreaking simulation, called TNG50, showed how dark matter isn't distributed evenly but forms intricate subhalos, mini clumps orbiting larger galaxies like moons around a planet. These subhalos are too faint to see directly, but their gravitational fingerprints appear in subtle distortions of lensed galaxies, matching real observations from Hubble and JWST. It's like uncovering invisible ink by studying how it warps the paper beneath. But simulations do more than confirm what we see, they predict what we've missed. In 2021, a team at Durham University ran a virtual universe called Hydrangea, focusing on how galaxy clusters grow over time. The simulation revealed an unexpected phenomenon. Lensed images should often contain faint, secondary arcs from dwarf galaxies orbiting the main cluster, features too dim for current telescopes to spot. When JWST later examined the cluster SMACS 0723, there they were, wispy, stretched smudges exactly where Hydrangea predicted. This isn't just validation, it's a roadmap guiding astronomers to hidden corners of the cosmos where dark matter's secrets might be hiding. The most tantalizing simulations explore edge cases. What if dark matter isn't cold and slow, as most theories assume, but warm and fast? Or what if gravity behaves differently on cosmic scales? By tweaking these variables, researchers create alternate universes, then compare their lensing patterns to real telescope data. One such experiment, the Eagle simulation, found that if dark matter interacted with itself even weakly, something most models rule out, it would smooth out the subhalos, making lensed arcs appear subtly softer. Real observations so far favor the classic cold dark matter model, but the mere possibility keeps scientists hunting for anomalies. Every warped galaxy image is a test case, a natural experiment probing physics no lab on Earth could replicate. What makes these digital universes indispensable is their ability to turn chaos into clarity. When the James Webb Space Telescope spots a bizarre, triply lensed supernova, simulations can rewind the scene, calculating exactly how the cluster's mass must be distributed to create that specific pattern. They act as cosmic Rosetta Stones, translating the distorted light of deep time into legible maps of matter, both seen and unseen. And as supercomputers grow more powerful, soon harnessing quantum processors or exascale architectures, they'll simulate not just how light bends, but how it interacts with every atom, magnetic field, and dark matter particle along the way. The ultimate goal, a perfect digital twin of our universe, where every reflection, every warped beam of starlight becomes a key to unlocking the past, present, and future of everything. Yet for all their sophistication, these simulations share a humbling limitation. They're only as good as our imagination. Every equation, every line of code is built on assumptions about how the universe works. When reality throws a curveball like a lensed galaxy that defies predictions, it's not just a glitch to fix, it's a clue that our cosmic story might need rewriting. That's the beautiful irony. To decode the universe's reflections, we've created reflections of our own, virtual laboratories where the cosmos can teach us in ways no telescope ever could. The simulations aren't just tools, they're mirrors showing us not only how the universe bends light, but how much we have left to learn. Dust isn't just cosmic clutter, it's the universe's foggy lens, a haze of microscopic particles that tints, scatters, and sometimes entirely obscures the light traveling through it. Picture trying to watch a sunset through a dirty window where every beam of light is softened, reddened, or blocked entirely by swirling motes. That's exactly what happens when starlight passes through interstellar dust clouds on its way to our telescopes. These tiny grains, no larger than a fraction of a human hair, are forged in the violent deaths of stars or the gentle outflows of aging red giants. They're made of carbon, silicon, and even ice, and they drift through space like fog banks, subtly altering the light that dares to traverse them. When this dust gets between us and a gravitationally lensed galaxy, the effects are doubly deceptive. Not only does the dust dim and redden the light, like turning down the brightness and adding a sepia filter, it can also distort the delicate patterns of lensed arcs and rings. Astronomers call this differential extinction, where dust clouds unevenly absorb certain wavelengths, making some parts of a lensed image appear fainter or more distorted than others. Imagine looking at a funhouse mirror smudged with fingerprints. The reflections are still there, but interpreting them becomes a puzzle. This is why tools like the James Webb Space Telescope, which observes in infrared light, are so revolutionary. Infrared slips through dust more easily, piercing veils that would completely block visible light. Yet dust isn't just an obstacle, it's a cosmic architect. Those same grains that obscure distant quasars are the raw materials for planets, comets, and even life itself. In the dense cores of molecular clouds, dust particles collide and stick together, forming pebbles, then boulders, and eventually the seeds of new worlds. The carbon in your DNA, the silicon in Earth's rocks, even the iron in your blood, all were once scattered atoms clinging to interstellar dust motes. When we see dust clouds silhouetted against lensed galaxies, we're not just looking at a nuisance. We're witnessing the universe's workshop where the building blocks of everything are forged. Decoding dust's influence is like learning to read through smudged ink. Astronomers use intricate models to subtract its effects, comparing how lensed objects appear at different wavelengths to reconstruct their true appearance. Sometimes dust even betrays its own presence in unexpected ways. The red halo effect, where lensed galaxies appear slightly redder at their edges, reveals dust clouds too diffuse to see directly. Other times, dust scattering properties create faint, light echoes, ghostly reflections of ancient supernovae that linger long after the explosion itself has faded. These echoes aren't just beautiful, they're clues helping us map the distribution of matter in galaxies we'd otherwise never see. The irony is profound. The very dust that obscures our view also holds the keys to understanding it. Without dust, there'd be no planets, no life to ponder the cosmos. Yet because of dust, the universe's deepest reflections will always be slightly out of focus, reminding us that every observation is a negotiation between light and shadow. Next time you see a Hubble image of a lensed galaxy streaked with dark filaments, remember, you're not just looking at a distant object, you're seeing the universe through its own dusty breath, a reminder that clarity is rare and that even the most perfect cosmic mirrors come with fingerprints. Neutrinos are the universe's stealthy messengers, tiny, nearly massless particles that stream through planets, stars, and even you at nearly the speed of light, leaving barely a trace. Billions pass through your fingernail every second, utterly undetected. Yet despite their ghostly nature, these particles aren't entirely immune to gravity's grip. According to Einstein's theory, anything with mass, even a neutrino's vanishingly small amount, warps the fabric of spacetime. The effect is unimaginably faint, but over cosmic distances, gravity can bend neutrino paths just like it bends light. This phenomenon, called neutrino lensing, could soon open a revolutionary window into the cosmos, revealing hidden structures even gravitational lensing can't touch. Imagine a neutrino born in the heart of a distant quasar, racing toward Earth for billions of years. Unlike light, which scatters off dust or gets absorbed by gas, this neutrino slips through everything: galaxies, black holes, entire galaxy clusters, as if they weren't there. But as it passes massive objects, its trajectory curves ever so slightly, leaving an imprint of every unseen structure it encountered. Future neutrino detectors, like the proposed P1 or IceCube Gen 2, could map these subtle deflections, creating a cosmic inventory of matter that light-based telescopes miss entirely. It's like turning the universe's shadows into a detailed blueprint, using particles that barely interact with anything at all. The potential is staggering. Take dark matter, the invisible glue holding galaxies together. While gravitational lensing reveals its presence through bent starlight, dark matter's finest details remain blurry, like a silhouette seen through frosted glass. Neutrino lensing could sharpen that image. Because neutrinos respond purely to gravity, their paths would trace dark matter's distribution with unprecedented precision, even exposing tiny subhalos too small to distort light. It's the difference between seeing a mountain range from afar and mapping every foothill and valley up close. Then there's the early universe. Light from the cosmic dawn is often obscured by thick clouds of primordial gas, but neutrinos from that era would arrive pristine, their paths subtly bent by the first protogalaxies. By analyzing these deflections, we might glimpse how the universe's largest structures began assembling, a story no telescope could tell alone. Even the cosmic microwave background, that ancient afterglow, might carry faint neutrino imprints, like whispers layered beneath a roar. But the real magic lies in synergy. Combine neutrino lensing with traditional gravitational lensing, and suddenly you're not just mapping matter, you're weighing it. Neutrinos would reveal how mass is distributed along their path, while light-based lensing shows how it's clustered locally. Together, they'd create a 3D mass map of the cosmos, exposing hidden filaments of dark matter or even exotic objects like primordial black holes. It's akin to diagnosing a patient with both X-rays and MRIs. Each method reveals what the other can't. Of course, the challenges are immense. Detecting neutrino deflections requires instruments of almost absurd sensitivity, capable of tracking particles with energies 1 trillion times higher than visible light. Current observatories like IceCube catch neutrinos by the handful, but to map lensing patterns, we'll need thousands more, with directional precision fine enough to spot deviations smaller than a hair's width on a football field. Yet the technology is advancing fast. proposed detectors would span cubic kilometers of ocean or ice, using Earth itself as a neutrino filter. This isn't just about adding another tool to astronomy's kit. Neutrino lensing could rewrite the rules of observation, proving that to see the universe clearly, sometimes you need to stop relying on light altogether. The same particles that pass through planets like their empty space might soon reveal those planets' deepest secrets, not by what they show, but by how they bend. In the hunt for cosmic truth, the most elusive messengers could become our sharpest eyes. Time behaves strangely in the cosmic hall of mirrors. While our everyday experience tells us time flows inexorably forward, eggs don't unscramble, coffee doesn't leap back into the cup, the universe's deepest reflections reveal a far more flexible reality. Physics treats past and future as fundamentally symmetrical, with equations that work just as well whether time runs forward or backward. Yet our perception insists on a one-way arrow, a stubborn directionality that seems baked into existence. Gravitational lensing plays with this contradiction, offering glimpses of events unfolding out of chronological order, as if the cosmos itself can't decide which way time should point. Consider supernova Refstal, whose explosive death played out multiple times across the sky like a cosmic rerun. From our vantage point, the sequence of images didn't follow the star's actual timeline. Some appeared years apart, with the final act delayed long after the others. It's as if we watched a film strip out of order, seeing the climax before the build-up. This isn't just a quirk of light travel times. It's a direct challenge to our instinctive notion of causality, proving that what we perceive as before and after can be scrambled by spacetime's geometry. The universe doesn't care about our linear narratives. It's happy to show us effects before causes, endings before beginnings. This temporal flexibility isn't limited to lensed supernova. Quasars flicker in and out of view as their light takes different paths around massive galaxies, arriving at Earth in sequences that defy their original chronology. In one striking case, astronomers observed a quasar's flare appear in one lensed image months before the others, like seeing a shadow before the hand that cast it. These distortions force us to confront an unsettling truth. Time's arrow might be less an intrinsic property of reality and more a side effect of our limited perspective, a trick of the mind as much as the cosmos. The implications ripple through fundamental physics. At quantum scales, particles routinely behave as if time's direction is negotiable, with experiments showing effects that appear to precede their causes. Cosmologists speculate that the Big Bang might not even be a unique beginning, but one phase in an endless cycle of expansion and contraction where time's arrow reverses with each new iteration. Gravitational lensing offers a macroscale preview of these possibilities, demonstrating that on cosmic scales, the sequence of events isn't fixed. It's a fluid tapestry, woven by gravity's hand into patterns that can loop, twist, and even knot. What does this mean for our understanding of reality? If lensed reflections can show us the past and present out of order, perhaps time isn't the rigid scaffold we imagine. It might be more like a river with currents that eddy and swirl when space-time bends. The universe's mirrors don't just reflect light, they reflect the malleable nature of time itself, offering glimpses of a deeper truth, that the distinctions we draw between past, present, and future are as much about perception as physics. Every warped supernova image, every out-of-sequence quasar flare, is a whisper from the cosmos, reminding us that the arrow of time is a story we tell ourselves, one that gravity is happy to rewrite. The wow signal cut through the static of deep space like a cosmic air horn, a 72-second burst of radio waves so intense that astronomer Jerry Amon circled it on the printout in red ink and scribbled, "Wow." Next to it, detected by Ohio State University's Big Ear telescope in 1977, this narrowband signal at 1420 MHz matched the predicted signature of an artificial transmission. Then, just as suddenly as it appeared, it vanished, never repeating despite decades of searching. While most scientists attribute it to a natural phenomenon, a passing comet's hydrogen cloud or a glinting satellite, its eerie precision still ignites speculation. What if we weren't hearing a direct signal but a reflection? A message from across the cosmos, bent and delayed by the universe's own mirrors. Gravitational lensing isn't just for light, radio waves like those of the WOW. Signal can also be warped by massive objects, their paths twisted into arcs that could scatter a transmission across millennia. Imagine a civilization around a distant star broadcasting a signal billions of years ago. As those radio waves traveled, they might have skirted a black hole or grazed a galaxy cluster, their trajectory bending like a pinball through cosmic bumpers. By the time the distorted echo reached Earth, it could appear as a fleeting blip, brief, directionless, and impossible to trace back to its source, the WOW. Signal's singular nature fits this unsettling profile, a message so stretched and scrambled by its journey that it barely resembles its original form. This idea transforms how we might search for extraterrestrial intelligence. Traditional SETI assumes alien signals would arrive via direct, intentional beacons, a cosmic hello aimed straight at us. But if civilizations arise at different times across the universe's 13.8 billion-year history, their signals could be reaching us through indirect routes, reflected off gravitational lenses we're only beginning to map. A transmission emitted when Earth was still molten rock might now be looping around a supermassive black hole, its echo finally curving toward us. These time-delayed signals wouldn't just be whispers from distant stars, they'd be postcards from epochs when our solar system didn't even exist. The challenges are staggering. A lensed radio signal would be fragmented, its frequency smeared by the Doppler shifts of moving galaxies or the expansion of space itself. Identifying it as artificial would require detecting patterns resilient enough to survive billions of years of cosmic distortion, perhaps repetitive mathematical sequences or pulses timed to universal constants like hydrogen's frequency. Even then, confirmation might be impossible. Unlike a lensed galaxy whose multiple images can be cross-checked, a one-time radio burst offers no second chances. The WOW signal's enduring mystery is a cautionary tale. The cosmos might be full of echoes we're ill-equipped to recognize, yet the tantalizing possibilities keep astronomers listening. Projects like Breakthrough Listen now analyze archival data for lensed signal candidates, while next-generation telescopes like the Square Kilometre Array will scan for repeating patterns in cosmic static. Some theorists even propose looking for stellar echoes, signals deliberately bounced off neutron stars or black holes by hypothetical civilizations using natural lenses as interstellar amplifiers. It's a dizzying thought that the universe's most advanced societies might not shout into the void, but whisper through its curved geometry, turning gravity into a galactic telecommunications network. Whether the WOW signal was a natural oddity or something more, its legacy endures as a reminder of how little we know about the universe's capacity to distort and redirect information. Every unexplained blip on a radio telescope isn't just noise, it's a potential reflection, a ripple in spacetime's pond that might have traveled longer and stranger paths than we can imagine. In a cosmos where light can bend, time can loop, and the past might still be out there somewhere, the line between signal and echo becomes beautifully blurred. The next time we detect a mystery from the depths of space, we do well to ask, are we hearing a voice or its ghost? Black holes have long been considered cosmic one-way doors, places where matter and light cross the event horizon and vanish forever. But what if these gravitational monsters aren't quite as silent as we thought? In recent years, physicists have detected faint ripples in spacetime that shouldn't exist according to classical relativity, gravitational wave echoes lingering after a black hole collision. These whispers from the abyss suggest that near the event horizon, spacetime might not be smooth and continuous as Einstein predicted. Instead, it could be frothing with quantum structures, a seething layer of microscopic loops or firewalls that bounce gravitational waves back like sound ricocheting off canyon walls. The implications are staggering. If these echoes hold up to scrutiny, they'd be the first direct evidence of quantum gravity, a theory reconciling Einstein's relativity with the bizarre rules of quantum mechanics. Picture the event horizon not as a clean boundary, but as a chaotic quantum storm where spacetime itself fractures into discrete pixels. Gravitational waves passing through this region wouldn't just disappear. They'd scatter, interfere, and sometimes rebound toward us as delayed signals, cosmic sonar pings revealing the hidden texture of reality. One leading hypothesis points to Planck stars, theoretical remnants from the early universe where collapsed matter rebounds at quantum scales. These ultra-dense objects hidden inside black holes could create a sort of gravitational echo chamber, trapping waves in loops before they eventually leak out. Another idea involves fuzzballs, string theory's proposed alternative to singularities, tangled knots of energy whose surfaces might reflect spacetime ripples like a drumhead vibrating long after being struck. The hunt for these echoes is already reshaping astronomy. Teams reanalyzing data from LIGO and Virgo detectors have identified tentative echo signals following major black hole mergers, like GW 150,914, the first gravitational wave ever detected. The timing of these echoes, arriving milliseconds to seconds after the main event, matches predictions for quantum structures just outside the event horizon. Skeptics argue these could be noise or artifacts, but the patterns persist across multiple collisions, hinting at something deeper. What makes this discovery so transformative isn't just the physics, it's how it redefines black holes as cosmic laboratories. These aren't just destructive voids, they're mirrors with memory, distorting and reflecting the universe's most violent events in ways that encode secrets about spacetime's fundamental nature. Every echo carries information scrambled by quantum gravity, offering clues about how information escapes black holes or doesn't, how singularities truly behave, and whether spacetime is ultimately pixelated or continuous. Future observatories like the space-based LISA mission could settle the debate by catching cleaner echo signals free of Earth seismic noise. A confirmed detection would do more than validate exotic theories. It would prove that black holes aren't the end of physics, but the beginning. They'd become windows into dimensions beyond our own, their reflections revealing layers of reality hidden in plain sight. The universe's darkest objects might ultimately be its brightest beacons, shining not with light, but with the reverberations of spacetime itself. On October 19, 2017, astronomers spotted something extraordinary, a visitor from beyond our solar system streaking past the Sun at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for scout, this interstellar interloper was unlike any asteroid or comet we'd seen before. Its peculiar shape, a tumbling, cigar-like object roughly 10 times longer than it was wide, sent researchers scrambling for explanations. Was it a shard of a shattered planet, a cosmic iceberg venting invisible gases, or, as one controversial hypothesis suggested, could it have been an artifact from an alien civilization, a solar sail or probe drifting between the stars. What made Oumuamua so fascinating wasn't just its origin, it was the story etched into its trajectory. This wasn't just a rock, it was a time capsule carrying chemical and physical clues from a star system we'll never directly observe. Every scar on its surface, every molecule in its composition, reflected an environment light years away, shaped by forces utterly foreign to our solar system. When telescopes caught glimpses of its reddish hue, a color often associated with organic, rich cosmic material, it hinted at the building blocks of planets, perhaps even life, forged around another sun. The real mystery lay in Oumuamua's unexpected acceleration as it departed. Most natural objects coast on gravity alone, but this one seemed to get a tiny, unexplained push. Comets do this when their ices vaporize in sunlight, creating visible tails, but Oumuamua showed no such tail. Some scientists proposed it might have released hidden pockets of hydrogen gas, while others speculated about more exotic possibilities. The absence of a clear answer only deepened the intrigue, turning this cosmic vagabond into a Rorschach test for astronomers. Everyone saw what they hoped to see, whether a fragment of a Pluto-like world or a relic of intelligence. Yet beyond the debate, Oumuamua offered something revolutionary, proof that our solar system isn't isolated. The galaxy is constantly exchanging material, hurling debris between stars like ships passing in the night. Simulations suggest such visitors might be astonishingly common, with thousands drifting through the solar system at any given time, too faint for our telescopes to spot. Future observatories like the Vera Rubin telescope could catch them by the dozens, each one a messenger from a different corner of the Milky Way. Imagine what we might learn from these nomads. A carbon-rich asteroid could reveal how organic chemistry varies in other star systems. A rogue ice ball might carry isotopes impossible to form near our Sun. And if we're extraordinarily lucky, one might even bear the unmistakable markings of technology, though the odds are vanishingly slim. The beauty of Oumuamua isn't in the answers it provided, but the questions it forced us to ask. This isn't just about studying rocks, it's about recognizing that the universe's reflections aren't limited to light. Sometimes they're physical, tangible pieces of distant worlds hurled across the void, waiting for us to piece together their origins. Every interstellar visitor is a puzzle wrapped in stardust, a whisper from a place we'll never visit, carrying secrets older than Earth itself. The next time one passes through, we'll be ready not just to watch but to listen. The universe has had 13.8 billion years to fill with life, yet we see no signs of civilizations beyond our own. This is the crushing silence at the heart of the Fermi paradox. But what if we're not just searching across space, but across deep time? Imagine a galaxy where intelligent species bloom like wildflowers in spring, each flourishing for a mere cosmic instant before fading away. The nearest civilization might not be 50 light-years away. It could have risen 50 million years ago, its radio signals now ancient echoes bouncing between the stars, its cities long reclaimed by nature or entropy. The problem isn't distance but timing. We could be surrounded by the ghosts of empires that died before Earth's first microbes stirred, their artifacts buried under layers of stellar dust, their signals stretched into unrecognizable whispers by the expanding universe. This temporal isolation transforms how we might find evidence of others. Traditional SETI listens for deliberate broadcasts, but what if the most revealing messages are accidental reflections cast by civilizations unaware they'd ever be observed? Consider the industrial pollutants a society might leave in its planet's atmosphere. JWST has already detected carbon dioxide and methane on distant exoplanets. What if it someday spots chlorofluorocarbons or nitrogen oxides, the chemical fingerprints of a long-dead industrial age? These wouldn't be signals meant for us, but cosmic shadows, lingering evidence of intelligence that burned bright and vanished. Even a civilization's waste heat, detectable as an infrared excess around its star, could outlive its creators by millennia, a thermal epitaph written in the afterglow of their energy hunger. The darkest twist lies in stellar archaeology. Advanced civilizations might reshape their environments in ways visible across cosmic time. Dyson swarms dimming stars, asteroid belts mined into unnatural patterns, or even stars moved for unfathomable purposes. In 2015, astronomers spotted KIC 8462852, a star whose irregular dimming defied natural explanations. While likely a swarm of comets, the speculation it might be alien megastructures ignited because such projects would endure. Unlike radio signals that fade after centuries, a Dyson sphere could orbit silently for billions of years, a monument to its builders' ambition long after their extinction. The universe's greatest irony might be that the easiest civilizations to detect are the ones already gone, their engineering projects outlasting their flesh and blood creators. Even our own artifacts could become these cosmic reflections. The Voyager probes, now drifting beyond the solar system, will outlast humanity by eons. The pyramids, though terrestrial, might survive as faint outlines in sedimentary layers long after Earth's surface is scoured clean by the sun's expansion. Future astronomers on distant worlds might study the unusual atmospheric composition of a long-dead Earth, puzzled by the spike in plutonium-244 in our geological record, a radioactive signature of our nuclear age lingering in rock strata. Our most enduring legacy may not be what we intended to send, but what we couldn't help leaving behind. This perspective flips the Fermi paradox on its head. The silence isn't proof we're alone, it's proof we're early. The universe only became habitable for complex life a few billion years ago, and stars will keep birthing planets for trillions more. We might be among the first civilizations to ask these questions. Our radio bubble's barely 100 light-years wide in a galaxy that won't hit its stride for another 100 billion years. Or we might be latecomers, sifting through the ruins of societies that flickered out when the Milky Way was young. Either way, the reflections we seek, whether in light, chemistry, or archaeology, aren't just messages. They're time capsules, bottles bobbing in the cosmic ocean long after their senders drowned. The paradox isn't that the universe is empty, it's that the universe is a graveyard, and we're only just learning to read the tombstones. Intergalactic pollution might sound like science fiction, but it could be the universe's most enduring tombstone. Imagine a civilization reaching industrial maturity, filling its atmosphere with synthetic molecules, chlorofluorocarbons from refrigeration, nitrogen oxides from combustion, or even exotic compounds we haven't invented yet. On Earth, these pollutants dissipate within centuries, but on a planet with slower atmospheric recycling, they might linger for millennia, imprinting themselves into the chemical strata of the air like a fossilized breath. Now picture a telescope like JWST analyzing the light filtering through such an atmosphere 10,000 light-years away. The spectrum wouldn't just reveal water or methane, it might show a jagged spike of tetrafluoromethane, a greenhouse gas with no natural source, screaming someone was here. These technosignatures wouldn't require aliens intentionally signaling us. They'd be cosmic litter, the equivalent of finding a plastic bottle washed up on a prehistoric shoreline. Take phosphine, a molecule detected in Venus clouds that, on Earth, is only produced industrially or by anaerobic bacteria. Its presence sparked debates about potential life, but what if future instruments find it alongside Freon-12 or perfluorocarbons? That's no ambiguous biosignature. It's a smoking gun for technology, a chemical fingerprint with no plausible natural explanation, the haunting part. The civilization that left it might have been dead for epochs, their cities dust, their languages forgotten. Their pollution would outlive them, a silent witness to their existence. The timescales are staggering. Earth's own Anthropocene layer, the geological marker of human activity, will likely persist in sediment records for millions of years. Now scale that to a type Roman II civilization harnessing its star's full energy. Their atmospheric alterations might dwarf ours, with megatons of artificial compounds absorbing specific wavelengths of light. Future telescopes equipped with high-resolution spectrographs could scan exoplanet transits for these unnatural absorption lines, turning atmospheres into interstellar autopsy reports. A planet with simultaneous spikes in sulfur hexafluoride and synthetic aromatics isn't just inhabited, it was engineered, and the engineers might be long gone. This transforms how we search for intelligence. Instead of listening for radio signals that fade after centuries, we'd look for industrial residues that endure for geologic eras. Dyson spheres might rust and space probes disintegrate, but a planet's atmospheric chemistry could preserve evidence of technology for millions of years. Even a civilization that self-destructed in nuclear war might leave a telltale mix of radioactive isotopes, krypton-85 from reactors or cesium-137 from bombs, detectable in infrared spectra. The universe wouldn't just reflect light, it would reflect choices, failures, and legacies written in atoms rather than words. Yet the darkest implication is this: the most obvious technosignatures might come from civilizations that didn't survive their own progress. A species mastering fusion could flood its atmosphere with helium-3, while one burning fossil fuels on a galactic scale might leave carbon-13 imbalances visible across interstellar distances. These wouldn't be hopeful signs of thriving societies, they'd be cosmic obituaries, warnings etched into the atmospheres of dead worlds. The same telescopes searching for life might instead become archaeologists of extinction, cataloging how often intelligence turns its home against itself. The beauty of this approach is its universality. Whether aliens breathe oxygen or methane, whether their technology runs on silicon or plasma, the laws of chemistry and physics constrain how their waste products interact with light. A chlorofluorocarbon absorbs specific frequencies whether it's floating above an Alpha Centaurian city or drifting through the ruins of an Andromedan megapolis. These molecules become Rosetta Stones, translating the rise and fall of civilizations across the cosmos into a language we can decode from a distance. So when astronomers debate where to point their next-generation telescopes, they're not just choosing coordinates, they're selecting which graveyards to scan. Every exoplanet atmosphere is a time capsule, potentially holding the last breaths of a species that reached for the stars and left behind a chemical cry into the darkness. The universe's reflections aren't just about what's out there now, they're about what was and what we might one day become. The idea that Earth's biosphere maintains its own equilibrium regulating temperature, oxygen levels, and even ocean salinity is radical enough. But what if this self-balancing act isn't unique to our planet? What if the entire universe operates under similar principles, with galaxies, stars, and dark matter conspiring in a cosmic-scale feedback loop to keep conditions just right for complexity to emerge? This is the Gaia hypothesis writ large, a theory that doesn't just place life within the universe, but frames the universe itself as a kind of living, self-regulating system. Evidence for this grand equilibrium hides in plain sight. Take star formation, the process that fills galaxies with light. On the surface, it seems chaotic. Gas clouds collapse, ignite, and explode, scattering heavy elements across space. But zoom out and patterns emerge. In dense galaxy clusters where interstellar gas is plentiful, stars form at a frenzied pace until the radiation from those newborn stars heats the surrounding gas, slowing further star birth. In quieter regions where raw materials are scarce, star formation ticks along at a steadier rhythm. It's as if the universe has a thermostat, dialing star production up or down to maintain balance. This cosmic self-regulation extends beyond individual galaxies. The largest structures in the universe, filaments of dark matter stretching hundreds of millions of light years, act like invisible rivers, channeling gas into galaxy clusters at rates that seem finely tuned. Too much inflow and galaxies would burn through their fuel too quickly, leaving the universe dark and sterile. Too little, and stars might never form in sufficient numbers to create the heavy elements needed for planets or life. Somehow, the system finds a middle ground, as if guided by an unseen hand. The most tantalizing clues come from the universe's chemistry. Life as we know it requires a precise mix of elements: carbon for organic molecules, oxygen for water, iron for planetary cores. Remarkably, the ratios of these elements across galaxies are strikingly consistent, as if something were calibrating the nuclear furnaces inside stars to produce just the right amounts. Supernovae, the violent deaths of massive stars, scatter these ingredients far and wide, but even their explosions follow patterns that suggest a deeper order. The universe isn't just making elements, it's curating them. If true, this changes everything about how we see life's place in the cosmos. Rather than a fragile accident clinging to a lonely planet, life becomes an expected outcome of universal self-regulation, a natural phase in a process that spans billions of years. The reflections we see in deep time-lensed galaxies, ancient quasars, even the cosmic microwave background aren't just snapshots of the past. They're pages in a story where the universe learns to sustain itself, experimenting with balance until complexity emerges. Perhaps the most humbling thought is this: if the universe can fine-tune its own evolution, then life might not be the end point. It could be a tool, a way for the cosmos to observe itself, to measure its own equilibrium, and maybe even steer its future. Every time we peer through a telescope, we're not just exploring space. We're participating in a feedback loop 13 billion years in the making, one where the universe uses eyes like ours to check its own reflection. Quantum entanglement already bends our intuition about space, linking particles so tightly that changing one instantly affects its partner, no matter how far apart they are. But what if this spooky connection doesn't just thread through space, but time? Recent lab experiments have revealed something even stranger. Particles can become entangled not just across distance, but across different moments in time. Imagine two photons created seconds apart, their fates intertwined so that measuring the later one retroactively determines the state of the earlier one, as if the universe is playing a game of quantum telephone between the past and future. This isn't science fiction. In 2022, physicists at the University of Chicago demonstrated temporal entanglement by splitting a laser beam and sending the photons through optical fibers of different lengths. Even though the particles arrived at detectors at slightly different times, their quantum states remained mysteriously linked. It's as if the second photon carried a message backward through time to its entangled partner, whispering instructions on how to behave before it was even measured. The implications are dizzying. If entanglement can stitch events across time, then the universe's fabric might be woven with threads that ignore our everyday notion of cause and effect. Now scale this up. If particles can be entangled across seconds, why not centuries or millennia? A civilization could, in theory, encode information in quantum states and send it forward or backward along these temporal threads, not by physically traveling through time, but by exploiting the universe's built-in quantum network. Picture a star-faring society planting entangled particles on distant worlds like cosmic time capsules, waiting for future explorers to read their quantum states and receive messages from the deep past. The data wouldn't travel faster than light. It would bypass time altogether, appearing instantaneously across epochs like a reflection in a mirror that shows both the past and future at once. Of course, the hurdles are enormous. Maintaining quantum coherence over long periods is like trying to keep a soap bubble intact in a hurricane. Even the slightest disturbance pops the delicate entangled state. And reading a temporal message without destroying its quantum information is like trying to smell a flower without breathing. Yet the mere possibility reshapes how we think about deep time. If quantum links can span eras, then the universe isn't just a collection of isolated moments. It's a living tapestry where every event might subtly influence every other, regardless of when or where they occur. The most radical idea, these temporal entanglements could already be all around us, hidden in plain sight. The cosmic microwave background, the afterglow of the Big Bang, might contain quantum correlations with particles in the present day, linking us directly to the universe's first moments. Black holes, those notorious destroyers of information, could preserve it in entangled states that leak back out over eons. Even dark matter, invisible and aloof, might participate in this quantum conversation across time, its gravitational whispers carrying echoes from epochs long gone. While we're far from building a quantum time telegraph, the science hints at something profound. The universe's mirrors don't just reflect light, they reflect possibility, weaving past, present, and future into a single, shimmering web. Every time we peer into the quantum realm, we're not just studying particles, we're glimpsing the universe's hidden grammar, a language where before and after might just be two sides of the same entangled coin. From gravitational lenses bending starlight into celestial mirages to quantum particles whispering across epochs, the universe doesn't just show us its history, it folds time itself into an endless hall of mirrors. Every reflection we capture, whether a warped galaxy arc or a time-delayed supernova, is more than a cosmic oddity. These distortions are nature's own forensic tools, letting us weigh the invisible scaffolding of dark matter, measure the expansion of space-time, and even glimpse the quantum tremors that seeded all existence. Consider how much we've learned from these accidental telescopes. Galaxy clusters acting as natural magnifying glasses revealed infant galaxies so distant their light has traveled over 13 billion years to reach us. Einstein rings, those perfect circles of warped starlight, became cosmic scales, measuring dark matter's grip with precision. Even fleeting anomalies like supernova rifts Dal, appearing multiple times around a gravitational lens, transformed into celestial stopwatches, proving that time itself stretches and loops under gravity's influence. The universe doesn't just hold these secrets, it bends its own light to help us decode them. Yet the most profound revelations might still lie ahead. Next-generation observatories like the Vera-Rubin telescope will scan the skies for millions of new lensed galaxies, while gravitational wave detectors hunt for echoes from black hole collisions that could rewrite Einstein's rules. Quantum experiments probing temporal entanglement suggest that spacetime's fabric might be stitched together with threads connecting past and future. Even the search for extraterrestrial intelligence is evolving, with astronomers now considering whether alien signals could reach us indirectly reflected off black holes or delayed by cosmic expansion like whispers bouncing between canyon walls. What makes these reflections so extraordinary is their duality. They're both artifacts of the past and portals to new physics. A single-lensed quasar image carries the imprint of dark matter structures it passed billions of years ago, while simultaneously testing whether dark energy's strength has changed over cosmic epochs. The cosmic microwave background, that ancient afterglow from the Big Bang, isn't just a snapshot, it's an active participant in the cosmos. Its photons still being subtly reshaped by galaxy clusters they encounter on their way to us. Every observation is a palimpsest with layers of meaning waiting to be peeled back. This interplay between light and time reshapes not just what we know, but how we explore. Traditional astronomy studies objects in space as they are now, but gravitational lensing lets us interrogate them as they were, and quantum experiments hint that the very act of observation might bridge those eras. The universe isn't a static museum exhibit, it's an ongoing performance where the lighting, the stage, and even the script change depending on where and when you choose to look. So when you step outside tonight and gaze up at the stars, remember, you're not just an observer, you're part of the universe's grand experiment in self-understanding. Those pinpricks of light aren't simply distant suns, they're messages from epochs when Earth didn't exist, carried across the void by a cosmos that bends its own rules to be seen. And with every new reflection we decipher, from the quantum to the cosmic, we're not just solving puzzles, we're learning how to converse with deep time itself. If this journey through the universe's looking glass has left you awestruck, don't keep it to yourself. Hit like, share with fellow space enthusiasts, and drop your wildest cosmic questions below. The adventure doesn't end here. With breakthroughs accelerating, the strangest reflections may still be waiting in the darkness, ready to rewrite everything we think we know. The cosmos is calling. All we have to do is keep looking and